saying one for all and all for one, no? And it means that both SUSY needs flavor, and flavor symmetries also need supersymmetry, as we will see. So let me try to explain a little bit what I mean by that. This thing, oh, better. Like this. Well, as you know, I don't know if supersymmetry exists at low energy. Okay, we have not been able to find it at the LHC, but for sure, I know that the flavor problem exists. No, we do have 3 generations of fermions in the standard model, and in fact, well, they are correctly described by the standard model. All observed flavor transitions can be accommodated simply in the Yukawa coupling. Some 3x3 matrices of the Higgs with in this case quarks, but with all the fermions, and with these Yukawa couplings are 3x3 matrices. Only the eigenvalues, the masses, and the mixings, the relative mixings in the left-handed sector are observable. But this is accommodated in the standard model. But you could ask, what is the origin of these Yukawa structures? Where do they come from? Why do we have 3 generations? Or why there is CP violation? Why there is a CP violating phase in the Kabibo-Kobayashi-Mascaba matrix? Well, to answer these questions is difficult if all we have are the masses and the CKM mixings. We can measure them more precisely, but I doubt that will help to understand, to find out what is the origin of these flavor and Yukawa structures. We need more flavor observables. Unfortunately, well, we do have also the electron sector that I did not put here, but we do have neutrino mixings and neutrino masses, but already we more or less know them. They are pretty different from the quark, but still we have already measured them. We need more flavor observables. This is what I have always hoped, and I still hope, that new physics can provide. In new physics, typically, they are not completely flavor blind. New physics typically contain new flavor structures. So in principle, we would have new observables that could help us to distinguish the origin of flavor. So one example of this new physics, I would say the best example is supersymmetry. But supersymmetry has what has always been called the SUSY flavor problem, okay? And also the CP problem, if you want. This has been always considered a problem because, well, you know, the soft-breaking masses in supersymmetry are fixed by or of the order of the mass of the gravitino. So in principle, you should expect in all the soft mass matrices, all the elements to be order of gravitino mass. Okay? If this was true, we would have a very, very severe flavor changing neutral current problem. Okay? In the same way, CP violation is also broken, and we could expect, we know in the standard model. So in an extension of the standard model, we could expect that all complex parameters can have order 1 phases. In that case, if you do it in supersymmetry, you have 2 large electric dipole moments. So we have 2 serious problems in supersymmetry, SUSY and flavor problem. But if you want, I would argue that the standard model has the same problem in the same terms. So fermion masses as soft masses are fixed by M3/2. So fermion masses, everybody knows, that are fixed by the Higgs spec, by the MW, if you want. So in principle, the more natural thing is to expect again that all the elements in Yukawa matrices, all the couplings times the BEP, all the couplings without the BEP are order 1. And in principle, all of them should have order 1 phases. So do you think the standard model with that, just without measuring masses and mixings, this is what I would do? And I would have a huge problem. It would be impossible to just writing the natural, in quotation marks, Yukawa matrices with natural phases to reproduce the observed masses, mixings, or CP violation. Okay? So for me, there is not a SUSY flavor problem, but there is a flavor problem, both in SUSY and in the standard model. So what can we do with that? Well, what I have always done from a long time ago is to try to understand the 3 generations of the standard model, the flavor problem, if you want, in terms of symmetry. Okay, here I am talking about flavor symmetries in supersymmetry, but again, it's the same in the standard model. I have been doing it lately in non-supersymmetric theories. I just have come back to supersymmetry in this work. But okay, in both cases, we have very, very different elements in Yukawa matrices. For instance, in the up quark sector, the top, the Yukawa of the top is order 1. The mass of the top is 174, 72. And the Yukawa of the up quark is 10 to minus 5. This is not natural. In a fundamental theory, we would expect all couplings to be order 1, not one coupling to be 1 and the other 10 to minus 5, 10 to minus 6, or for the neutrinos, much worse. So there must be some reason for that, for these couplings to be that small. The small couplings are typically generated as a function of small BEPs, power of small BEPs, or perhaps loops. In loop, you have a suppression of alpha, so you can get a small number like that. This one of the best, or the best idea to explain these things is the Froggatt-Nielsen mechanism with a flavor symmetry. This is done like that. This is an example of a diagram. This is in supersymmetric notation. The arrows mean that they are superfields, but okay, whatever. You have a left-handed fermion and a right-handed fermion, but they have different charges under another symmetry. This case, I'm talking about U1 flavor, okay? This has charge 0 and this has charge 1. The Higgs has also charge 0. So you can never have an invariant coupling Higgs right-handed, left-handed. But there is another field, and at the end, if you talk of fermions, would be a scalar, which is called flavon, that gets a vacuum expectation value. And this field had charge -1. So there is some mediator mass here. And at the end, this diagram, once you integrate this large mass, gives you a coupling which is theta over m. The BEP over the mediator mass. And this is a dimensionless coupling, the Yukawa coupling. And then when this gets a BEP, this gives the mass. This is the idea of Froggatt and Nielsen. If you have charge 2, you would need the 2 insertions of that. So the mass could be even smaller. That is the idea of a flavor symmetry. And this can explain the small numbers in the Yukawa couplings. Now, I am talking of supersymmetry. I am saying that this flavor symmetry can explain the masses and the mixings in the Yukawas. The Yukawas are forbidden by the symmetry and generated only after spontaneous symmetry breaking. But if we are in a supersymmetric theory, the symmetry applies to the full theory, not only to the fermions, but to the fermions and to the scalars, for instance, to the quarks and the squarks, to the fermions and the fermions. In that case, if we are talking of scalars, diagonal soft masses, diagonal couplings, phi dagger, are obviously neutral under any symmetry, because phi has obviously the opposite charges of I dagger. So this will be always allowed. So the diagonals of masses are always allowed. But the difference in the masses and the non-diagonal elements are proportional to symmetry breaking in supersymmetry. In that case, we can relate the structure of the Yukawa matrices to the non-universality in the soft breaking masses, soft breaking terms in general. And then this is an example of new physics that can give us new information of flavor. If Yukawa matrices and soft terms are not simultaneously diagonalizable. The question, well, you know, there was, if you are old enough like me, the constrained supersymmetric standard model where all soft terms were proportional to the identity. So you can diagonalize simultaneously the soft masses and the Yukawa matrices. But I try to argue here that this is not the usual thing, especially if you think of supergravity mediation, well, high scale mediation. So what I talk here is, let's think of the Yukawa couplings or the standard model as an effective theory of more complete theory at higher energies, which includes these Froggatt-Nielsen fields. Obviously, it's what I was saying before. I have all these couplings and a heavy mass for these chi's here. Once I integrate out these fields, I get just the Yukawa coupling, dimensionless. Okay? No, so what happens with the soft breaking terms? Huh? In the soft breaking terms, we can start with flavor universal SUSY breaking, just a single F term in this case that breaks supersymmetry coupling to different couplings. But even with this would be the usual thing in supergravity, in this constrained NMSSM. But if you do that to the standard model, you would get everything universal. But if you do it to the fundamental theory with the Froggatt-Nielsen mediators and flavons, you have this. You can put the F term, F term, this insertion breaks supersymmetry, and this would give you a contribution to a, in this case, trilinear coupling. But you can, in the effective theory, you can put this SUSY breaking coupling here, or you can put it here, or you can put it here, or you can put it here or here. So in total, there are 5 ways where you can put the SUSY breaking F term. And once you integrate out the heavy fields, this contributes to the same trilinear coupling. In that case, in this coupling, you have a factor 5 for the SUSY breaking. But if you have only 2 insertions, 2 flavon insertions, instead of 1 flavon insertion, instead of 5, you would have 3, for instance. So it's a different factor depending on the element of the Yukawa matrix, if you want. So they are not universal. The same happens with the kinetic terms and the soft masses. This would be a correction to a kinetic term, mixing phi3 and phi0, but with flavons. But if you put 2 F terms like this, 2 X fields, Fx in this case, you generate a contribution to the soft masses. You can put them in very different places, here, or even one entering and one exiting. This is a D term, so it must be one entering and one outside of the vertex. So you can put it in many different ways. And again, if you integrate it out, at the end, there would be a factor n, the M0, which is just the F of X, the value of the F term of the X field, times these flavons. But you can put this M0 square in n different places, so you have a different factor. In that case, the soft mass matrix is not proportional to the, in this case, kinetic terms because you have, or the trilinear coupling is not proportional to the Yukawa couplings. So let's see an example. The easiest example is an abelian flavor symmetry. For instance, in this case, I am putting for the quarks these charges. 3 for the first generation left-handed doublet. No, yes, doublet. 2 for the second and 0 for the 3. And for the ups, these charges. The same for the down, these charges. And a flavon with charge -1, such that the BEP of this flavon over the mediator mass is Cabibbo mixing, order of Cabibbo mixing. In this case, the down quark mass would be λ4, λ3, 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 λ2, λ2, λ1, 1. And the up quark mass like this, 1, λ4, λ6, okay? And this roughly, not exactly, but roughly reproduces the observed hierarchy and the observed mixings in the quarks. Now, if you do the same with trilinear couplings, and I did before, you will see that you get these large factors here. 7, 9, 1, in this case 13, because they are very big, a lot of insertions. Here they are 6 insertions, okay? And obviously, once we go to the basis that diagonalizes this Yukawa matrix, the trilinear couplings are not diagonal. So even not diagonal, but they preserve the same powers of lambda with some factors. In this case, as we had in the flavor basis. So in this case, we would have non-universal soft masses, trilinear couplings, that we could measure at the LHC if someday we can produce the supersymmetric particles, which are, if they are not too heavy. I hope they exist, although they may be heavy. So the same happens with the soft masses. As I was saying, a coupling like that, phi I dagger, is invariant under any symmetry. So it's always allowed by any flavor symmetry you can put. But in this case, if we put a single F term, breaking SUSY, all the diagonal masses are not only allowed, but equal, as it's required by phenomenology. But of diagonal entries are proportional to the flavon BEPs, as we were saying. Moreover, they are not proportional to the kinetic terms. This of kinetic terms is because, you know, you have to consider also the corrections to the kinetic term of the fermion of the scalar in this case. Okay, and this is what is called in the standard model wave function renormalization. These are the corrections to the kinetic term. In supersymmetry, we call it the Kähler potential, but it's the same. What you have to do, what you do with wave function renormalization is redefine the kinetic terms to be again canonical. This is what is called canonical normalization. That is, you have to diagonalize the kinetic terms and rescale the diagonal elements to again get 1, 1, 1, and the usual kinetic. And this has to be done with all the couplings, all the fields in it's canonical normalization. It's wave function normalization with all the fields in the theory. And this changes the softmax matrices. Before canonical normalization, it was like this. After canonical normalization, it's reduced, but it's not the identity. Again, if we produce this softmax, these quarks and up and down quarks, we will be able to measure this. And for instance, if in the standard model, we can only measure left-handed mixings. That would be one of these. But in MSSM, we will be able to measure, if we measure it sometime, also the right-handed mixings. We would be able to say if the Yukawa couplings have non-trivial right-handed mixings or not. All we need is another matrix to compare, obviously, the Yukawa couplings. Okay, this was an example with a simple abelian symmetry. This is another one which we work along many times. Is a discrete non-abelian symmetry. This kind of symmetries are very common in neutrino masses. Why? Because in neutrinos you have typically large mixings, and large mixings imply that you require some webs of this kind, some symmetry between different elements of a non-abelian of a vector. So this was a symmetry that we were using both for quarks and leptons, and is more or less complicated with the quarks. I am putting here just the leptons, leptons and neutrinos. The Higgs, some other field, and these are flavons. Okay, these flavons get this kind of webs: 0, 0, 1, 0, 1, 1, or minus 1, 1, and 1, 1, 1. Okay, with different webs. And choosing this kind of vacuum expectation values, the V3, this one, to be of order square root of the Yukawas, because of the Yukawa of the tau, I mean, because at the end you want here Yukawa of the tau, and these others, epsilon times the Yukawa or epsilon square, you get this kind of charged lepton Yukawas, which are quite good for the masses and mixing. And at the same time, as I was saying, again, if you do what I was doing before, or of an effective theory of inserting the F term in all the possible ways in the fundamental theory, you get different factors here. And then this is not proportional. When this is diagonalized, this is never diagonalized. Okay, so we will be able to measure here if we measure the submasses and the couplings of the leptons, we will see what kind of symmetry generated them. Okay, the same for the softmass matrices. The softmass matrices in this case are of this kind times M0. This is the SUSY breaking scale, whatever, M SUSY if you want. And after canonical normalization and going to the super CKM basis, the basis where the Yukawas are diagonal, you still get something of diagonal that you will be able to measure at the LHC. But here comes one comment. I was saying at the beginning that supersymmetry has a problem. We had a problem normally, the flavor problem. The flavor problem said that in principle in these mass matrices, in the softmass matrices, you expect all the elements in the mass matrix to be order 1, order M0 square. Okay, but here you see, as the diagonal elements are order 1, they have sometimes corrections like these ones, but I are order 1. But the diagonal elements are proportional to the flavor symmetry breaking. So this of diagonal element is not 1, is epsilon square, Habibo square if you want. And so, in principle, they are more controlled than in a just arbitrary theory where you put all couplings 1. What happens also in the standard model, as I was saying. So, a flavor symmetry here is solving the supersymmetric flavor problem, if you want. But at the same time, is allowing us to have a new flavor observable that can help us to determine what is the symmetry responsible for these 3 generations and flavor masses and mixes. Okay, for instance, in this case, this was done for leptons. I was doing it for lepton flavor evaluation. And mu gamma and mu 3 are very sensitive, even with heavy sphere. Here we were saying that even for very heavy fermion fermion masses. This is the gaugino mass of order 2 TeV, even 10 TeVs, and very heavy scalar masses, which is M0, up to 10 TeVs. You could still have some in this model. And this is for this delta 27 model with some tangent beta 20 and some assumption on the V1 to 3 over the mediator mass. And you can see the present bound of mu gamma is this one here, this blue region. This could be in this model if there is a CP phase order 1 in the soft masses, the contribution from the constraint from epsilon k, the difference from epsilon k to the standard model value. But in the future, the branching ratio mu3 larger than 10 to minus 16 could reach this region here, or the mu e conversion in nuclei larger than 10, smaller should be, no? Than 10 to minus 7. Ah, no, the larger is this region, yes. Could explore all this region, okay? So they are very, very sensitive to this kind of flavor symmetries, to supersymmetry, if there is a flavor symmetry controlling the flavor in supersymmetry. Well, so that, this is more or less the middle of my talk. I was saying that these flavor symmetries can solve the CP and flavor problems, both in new physics and the standard model, and they can provide very valuable information on the origin of flavor. We expect non-universality always to be present at some level. I was saying here, or I said it fast, that in supergravity, you typically expect this to be order 1. If it's some other, could be gauge mediation or things like that in supersymmetry. I don't know if you know these terms. Supersymmetry is not very much in fashion anymore, but okay. There can be other ways where this is reduced. It's still present, but can be smaller. And well, these flavor structures remember the structures of flavor bases. And there is a large reach in interesting models. However, as I was saying, unfortunately, so far, no supersymmetry has been found at LHC or, if you want, in indirect experiments. So, is SUSY still of any use? And this is my second part, the second part of my talk. I will try to convince you that there is still something where SUSY is very useful. And this is in the vacuum alignment or in flavor symmetries, okay? In flavor symmetries, we have seen the delta 27 example before. We need a very, very particular direction of the flavon webs. These are triplets of a flavor symmetry. It's non-abelian symmetry. The more natural thing, if you want, is to assume, as there are 3 generations, that there is one single field with 3 components. This is a triplet, okay? And to generate the structures, you typically need, especially in the neutrinos, you typically need these flavons which have equal webs in all 3 components, or 0 in one and equal in other 2 components, or just in one and the rest 0. Okay, but this kind of alignment is not easy to obtain in a non-supersymmetric theory. You know, for sure, Antonio will know. Most of these models, the alignment is done in supersymmetry. Most of these models of flavor symmetries are done in supersymmetry. And why? Because I told you, in, say, the last 2 or 3 years, I have been doing flavor symmetries without supersymmetry. And now I wanted to do something to generate this kind of alignment in a non-supersymmetric theory. And I found a huge problem. It was impossible. Why? Because In particular, it's very simple. In principle, all you have to do is to write a scalar potential, for all the scalar fields. These are flavons, these are also scalars like the Higgs, okay? But these are typically triplets, or in some other theories, can be even 5-plets or 10-plets or many components. Some doublets also in some theories, or singlets. But you have to get, for them, these kind of alignments. And for that, you have to build a particular potential that once you minimize it, gives you this minima. This is, I would say, impossible to do if you write a non-supersymmetric potential just in terms of symmetries. Why? Well, as I was saying, I said it for the soft masses, but all the quartic couplings like this, phi I, phi j, this is a product of two triplets. Can be another triplet or a singlet or maybe a sextlet or whatever. I don't care. Whatever coupling I write here, being a triplet or a singlet, if I do moduli square, it's always allowed. It will be always present in the scalar potential, always. I can do nothing. For symmetry, all these quartic couplings are allowed. The same happens, well, with the quadratics. Well, depends on if they are singlets, obviously. But they must be, obviously, the scalar potential must be singlet under the symmetry, okay? But if I try to do it like in non-supersymmetric theory, well, all of these, in principle, are allowed by symmetry. So I want some of them, but not all of them. I just want a couple of them that can give me this alignment. The rest will destroy this alignment. So, well, yes, they are allowed, but they can be very small or they can be zero. But I have to do it arbitrarily. There is no symmetry that can forbid these couplings, okay? Yes, I can do it, but I don't like it, okay? So then I went back to supersymmetry. What happens in supersymmetry? Supersymmetry, this is one thing. The scalar potential in supersymmetry is much more restricted than in a non-supersymmetric theory. The scalar potential comes from the superpotential. Well, there's also contributions from the D terms, but for the moment, I will consider only the superpotential. The superpotential is a cubic function of the superfield, singlet under all the symmetries of the theory, okay? So the scalar potential are the F terms, F dagger, of all the fields in the superpotential. So it's a sum of the derivative of the superpotential with respect to the field phi n, and the same dagger, okay? So in this way, this is what is usually done in supersymmetric theories. It is possible to select some of these flavon bilinears that I was saying that all of them moduli square are allowed. Now I can select which ones are allowed and which ones are not. I am selecting them with some driving fields, some extra fields that I call capital phi n, with the appropriate charges, just the opposite charges of the bilinear I want to select, okay? So the superpotential will be a sum of some driving fields times a bilinear of the flavons, which has opposite charge to the driving field. These driving fields really are only used for this. They appear only linearly in the superpotential. If they appear linearly in the superpotential, you can guess that you can derive any of these other fields for the FMs. You must do it, and some for the scalar potential. They will appear at most quadratically in the scalar potential here, okay? And if they appear only quadratically, it's very easy to see that if the quadratic coefficient is positive, they will get always 0 beta. Okay, so these driving fields are only used for this. At low energies, they are heavy in principle, they are high energies, they select whatever bilinear you want, and then they get zero BEP, they disappear from the low energy field. They have no other. But like that, you can obtain the scalar potential you want. In fact, in supersymmetry, as you see, this is moduli square of F, sum of moduli square. Moduli squares are positive. Okay, so the minimum of the supersymmetric, any supersymmetric potential is zero. They cannot never be negative, a supersymmetric potential. Okay, so the minima is when the F terms are zero. All you ask is for vanishing of the F terms. Okay, in fact, of the driving field F terms, because any other F term will invoke a driving field with zero vacuum expectation value. So you only have to consider this. Let's see an example. I am doing here a very simple example. It has some technicalities, but I won't talk too much about them. This is a possible superpotential. Here, what I'm doing is I have two fields, phi A and phi B. Okay, and I am arbitrarily, if you want, arbitrarily in quotation marks, by some other field that gets some other BEP at high energies, I am putting here some BEP. Once I do F of A, I have it here. F of this A and B is the derivative of this with respect to phi 0, capital phi 0, A or B is lambda phi A squared, singlet, minus x squared. Obviously, this is 0 when the BEP of this is x squared, no? So this fixes the size of phi A and phi B. And then I have this other coupling, lambda C, which makes that phi A times phi B with this mediator. If I do the derivative of the superpotential with the mediator, I get the F term, which is okay, phi A times phi B is 0. That is, they are orthogonal. Okay, then there are these other couplings, triplets, which we did it to select that only one of the components of phi A and phi B are different from 0, because here you can see that, well, we have 3 derivatives here from D or E, well, 6 in this case, and they choose that always 2 of them, not this one, but the rest are 0 at the end. This gives us this kind of BEPs, just for the vanishing of the F terms. Much simpler than minimizing the whole scalar potential, but for supersymmetry it's the same. Okay, so, well, obviously here I could have put the XA in the first, second, or third component, but this is just a movement, a reshuffling of the BEPs, nothing special. But like this, I can fix the BEP in supersymmetry. That's the problem, in supersymmetry. The question is this one. Can we use this same technique? Can we preserve this alignment in a non-supersymmetric model? Now, in fact, that was in this world, that was what I wanted. I didn't want a supersymmetric theory. I wanted a non-supersymmetric theory to have some particular alignment, but I could not. So can we preserve this alignment starting from SUSY? Yes, that's what I'm going to tell you. Well, we can have supersymmetry broken at a higher scale. For instance, imagine that we have a supersymmetric model, but the soft breaking is broken such that the masses of the gauginos and the soft masses are, I don't know, at 100 TeVs or at 10 TeVs. So obviously the theory we see at low energies is non-supersymmetric. Okay, and we would see some scalar potential if you want, if the breaking is at lower energies, which I don't think, but okay. we could see some flavon alignment if you want, but we could not understand where does it come from without supersymmetry. In this case, so let's try one thing. We start from supersymmetry, from the things I said the previous transparency, but now I put, apart from the supersymmetric scalar potential, which is just the sum of the F terms, as we were saying, here, well, if you want, from this supersymmetric potential, you can do the derivatives. If this square, you can check that all you will have is either quadratic or quartic. This one gives you a quartic coupling in the scalar potential, moduli square of this with lambda square, yes, but moduli, this is a quartic, and here we will have x squared times one of these or one of these conjugated, which would be a quadratic, okay? So in this model, in particular, we have only quadratic scalar potential with two fields, two flavon fields, or quartic, okay? And this would be this supersymmetric, and I add the soft-breaking masses, some masses that do not come from the superpotential. The superpotential gives masses both to scalars and to fermions, and the same masses. This is the idea of supersymmetry, okay? While the soft-breaking masses contribute only to the scalars, but not to the fermions. So they break the symmetry, okay? So in that case, from the previous superpotential, I will have some mass from quadratic terms of this kind, phi I square and phi I dagger square times MA. Plus this is the quadratic, plus the quartic potential, which are just 4 flavons, plus now another quadratic term, which are the soft masses, okay? Well, as I was saying before, but now I will use some general discussion. Do not need to go to the particular superpotential or to the particular scalar potential. What I'm doing is, in the supersymmetric minima, well, here, the minima correspond, as I was saying, to vanishing F terms. The F terms are 0. And in particular, if all the couplings in the superpotential are real, obviously the verbs that make these F terms 0 will be real, okay? So from now on, I will forget about the daggers, about the stars that I was saying here, okay? That was to simplify. I could do it, but it's simpler like that. I could keep the imaginary and the real, but I'm not interested, it's too long, okay? So now I have to minimize first the scalar potential to find the supersymmetric minimum, the supersymmetric scalar potential. Obviously, I minimize this part, m squared plus v squared. And I get that from here, I get the 2, I get ma squared phi a. This is a means representation, and the I is the component, but okay, forget. Just some mass times some field in the supersymmetric minimum plus the derivative of the quartic potential, quartic terms with over this derived with the same field in the supersymmetric minimum. This must be 0. This is the condition for minimization of a potential, okay? The derivative with respect, all the derivatives with respect to any field must be 0. And this implies this part here, that the quartic, the derivative of the quartic coupling with respect to phi in the minimum must be minus ma squared phi, okay? Now, I want to preserve the supersymmetric vacuum in the full potential, in this full potential with non-supersymmetry, with supersymmetry breaking, with this terms extra, okay? If I want to preserve, I will want that the verb in the full minimum is just some rescaling, this zeta is a rescaling of the verb in the supersymmetric minimum, which is this one here, okay? So now I minimize the full scalar potential, okay? I do the same thing. The derivative of the potential with respect to any field must be 0. I get this equation. And now I can write this thing that in the minimum, when this is in the evaluated in the minimum, this must be minus the two terms here. Okay, but again, now I can use that the quartic potential is quartic in the fields. So it has 4 fields. If I make one derivative, it has only 3 fields. So it will scale from the BEP that has in the full potential. If I have just a rescaling of the BEP, will be Z cube the BEP, the derivative in the supersymmetric potential. But the derivative in the supersymmetric potential, we knew from here that was minus the mass square, the supersymmetric mass square. Then minus Z cube MA square phi in the supersymmetric minimum, but phi Z times phi in the supersymmetric minimum is equal to phi in the full minimum. And therefore, I can replace this part, this by this in this equation. And I get this condition here, all in the full minimum, okay? That the BEP mu, the subbraking mass times the BEP must be this thing, or equivalently, the scaling is done by this. This is true if mu is the same for all the components of the field. But this is just a way to rescale to obtain the rescaling. And more importantly, this is exact. I have done no approximation here for this case. This is the SUSY alignment is maintained exactly for, well, I had not said it before. I am assuming so far that the soft masses do not break the flavor symmetry. The flavor symmetry is broken spontaneously. If not, all what I said at the beginning would be meaningless. Obviously, I was saying that the soft masses, the non-universality in the soft masses is related to the breaking of the flavor symmetry. So in this case, SUSY alignment is maintained exactly if we work with invariant subbreaking mass. And I have been able to calculate exactly which will be the rescaling of the BEP once I add the soft masses. But even more, even if I do non-invariant subbreaking, there are some conditions where the alignment can be maintained. Now I'm adding to the supersymmetric minimum some non-universal. Now it depends, it's a matrix of mass and depends on the indices K and J. So we have this potential. I do as before. I do the derivatives as before. I replace the derivative of the quartic potential, and I arrive to this equation here. This is not anymore necessarily true. This is a matrix times a vector equal to the same vector. If I put this as a vector, I forget about the indices. This is a matrix times a vector is a number times the same vector. So this means that, but if this is the condition that has to be satisfied if we want to preserve the scaling, even in this case. We can still preserve the vacuum alignment if and only if the SUSY BEP is an eigenvector of the SUSY subbreaking matrix. Okay, this is the SUSY subbreaking matrix, and if this is an eigenvector, then the alignment is still preserved. Okay. Well, this is what I wanted to do. I wanted to find out, or to be able to build a model where I can still use the supersymmetric techniques to determine the flavor alignment, but keeping the BEP alignment even for very large SUSY breaking. I can do it not only for very large, I can do it exactly. In these cases, these are somehow particular. There are some special cases that I have not discussed, obviously. But this is what I wanted to say. I arrived to my conclusions. As we were saying, the first in the first part, supersymmetry can be very useful, or new physics in general, can be very useful to help us to understand the origin of flavor. In particular, supersymmetry has always non-universals or breaking terms, which can provide us very important information on the symmetries responsible for the flavor in the standard model in nature. Okay, but even if supersymmetry is not present at low energies, supersymmetry is a very complete theory. It has very nice properties, symmetries, if you want. Okay, and these nice properties can help in many things, can be exploited in other things. As we were saying it in the flavon sector, you talked about supersymmetric vacuum alignment, which is very easy to build in supersymmetry, but it's very difficult in non-supersymmetric theories. And as I was showing here, supersymmetric vacuum alignment can be preserved in softly broken theories that apparently are non-supersymmetric at low energies, as a standard model, for instance. Okay, so this is what I wanted to say, that SUSY needs flavor, a flavor symmetry, and flavor needs supersymmetry for both. So this is basically all I wanted to say. I have some other things if you have questions.
Thank you very much, Oscar, for the very nice and complete talk. Question from the audience? Questions? Oscar, I had a question in the plot that you show for these different constraints from epsilon K and CLFB. What about the constraint from the B meson? Or the B meson weaker constraint than the K meson?
Yes. Well, you know, a long time ago when we started in this business of supersymmetry, there were the B factories that had a large discrepancy from the expectations of the standard model. But then looking at these things, I realized that in K sector, for instance, the imaginary part is much smaller, 10 to minus 5 than the real part in KK bar mixing. While in the B sector, it's not like that. They must be of the same order, okay? And in that case, you need very large CP violation there, and it's difficult. It's possible, but typically with SUSY masses a little bit higher, in this case, you see, epsilon K over epsilon is competitive with mu gamma, but only if you assume that there is one order, one phase, which is not easy at all either in these symmetries. I was just assuming that is the off-diagonal element in the KK bar matrix, but has an order one phase. Typically, this is not like that. You have to rephase the elements, and these phases would be subdominant. In the case of the B sector, is the same. You have to rephase the CKM, and then as the phases are related from the CKM and the soft matrices, typically the phases are smaller. And in the B sector, it's much more difficult to get a large phase than in the K, well, a large effect that in K sector. For me, the best observables still are lepton flavor violation.
I see. And for the electron flavor violation, but what about electron muon conversion, but in the titanium, or the bound is weaker than in aluminum?
Yes, I don't remember now. This is a plot from a paper a couple of years ago. Maybe something should be updated also. But yes, I think this was the strongest bound at that time. But it's just an example. It will be of the same order. But in these cases, again, you can reach with these experiments very heavy masses. It's true that you could be here. For instance, here you see the lepton masses. This was 60 eV, typical lepton mass, and this is the gluino mass to give an order of magnitude of what you could expect. This would never be able to. You will never be able to see this in LHC. in these indirect experiments, you perhaps can see something. I still have the hope that we can see something in this lepton flavor validation experiment. Although, on the other hand, it will be very difficult to say which symmetry is responsible for them, obviously, if you see just mu-E conversion or mu-triple-E, no?
I have a question.
Yes.
How many parameters do you have in your model? See that you have many self-breaking terms.
Yes, but no. Well, let me see. What I was saying here, yes, in principle, in my model, I have one self-breaking term, not many, M0, Fx if you want, okay? The thing is that I have many elements in the Yukawa matrix or in the trilinear or in the submatrix like this. I have many elements, true, but all of them are determined by the symmetry. The only thing unknown given this symmetry here is M0. The other, well, there are still order 1 parameters. That's the usual typical thing because you don't know. If we come here, obviously, if I knew the coupling, this coupling here and this coupling here and the masses, I could calculate exactly this diagram, but I don't know. I only see the effective theory, okay? All I am using here is that the charges I need from here, the charges of these fields are like that. This is charge 3, this is charge 0. And this implies that I have 3 fields there, okay? But I don't know the mass. I am guessing just that the masses of these, x2, this has charge 2, this has charge 1, this has charge -1, or whatever. And these ones have the same order mass, but they can be factors of order 1 of difference. So in that sense, when I talk about these matrices, for instance, I am putting here just 1, but this instead of 1 could be, I don't know, 2.5 or 0.7. I would not say this is a failure of the model, but I would have to measure. I only predict that this is 1, and this one is epsilon cube. That is Cabibo cube. That is 10 to minus 2 or whatever. Okay? But in that sense, I do have unknown parameters to measure, but not so many free parameters, given the flavor symmetry. Huh? I can have many different flavor symmetries that give me different predictions. Huh?
It seems that you're only talking about quarks and not leptons, right?
Well, there I was talking about quarks. Now I am talking about leptons, but it's the same thing, yes. It's the symmetry is similar. Huh? The structure...
different parameters.
Yeah. They are different parameters, for sure. Here I am talking about quarks, if you want. The same thing, eh? These factors...
What about the other supersymmetric particles? I mean, where are they? I mean, are they...
Yeah. Well, you know, for sure, I should have Gaugino masses also. Huh? All the Gauginos have a mass. I should have also the mu, but here I was concentrating only on the parameters affecting the quark or lepton mass matrices. Okay. Yes, there are corrections to this one proportional to the Gaugino masses also, but they are flavor universal. Okay, these are the non-universal. If I put this, I have done it many times in a full model, I should break this flavor symmetry maybe at a higher scale that could, well, the scale is not determined, but could be typically people put it at the gut scale, okay? And then from there, I should do the running of all the parameters. I get corrections proportional to Gaugino masses, to the gluino mass and everything, to the diagonal elements. But still, this reduces slightly the flavor, well, the size of the flavor changing effects, but still they are there. and they can be measured.
But you're talking about the minimal supersymmetric model, but that has been ruled out. I mean, so what version of supersymmetry are you talking about here?
Yeah, I am talking about the minimal supersymmetric standard model, but with a flavor symmetry on top of it. If you want.
The experiment.
What?
That has been ruled out by experiment, the minimal supersymmetric model.
No, well, more or less. Yes, but depends on what do you mean, but it's been ruled out. It's not been found. But you can put the masses as high as you want of the supersymmetric particles. That's what I am doing in the second part of my talk. You can put M0 equal 10 TeVs, and it's not being ruled out 10 TeVs, no?
Well, my understanding has been ruled out to experiment. I mean,
no, I would not say so much. Yes, it's true that it's getting less and less interesting. Yes. We would have expected to have found supersymmetry already at these scales. But I could not be too worried instead of 2 TeVs or 3 TeVs, the masses. Okay? It could be still accepted. True that being 10 TeVs implies that to predict the mass of the Higgs in supersymmetry, just in the minimal supersymmetric standard model, is very difficult with that. Yes, you can do it, but with a large fine-tuning, which is what supersymmetry wanted to avoid. In that sense, it's getting less and less attractive. Yes, I agree 100%, but still is what I was saying here. Even if it's not observed, there are properties of SUSY that are very, very useful, and I believe still that they may play a role even at high energies.
More questions from the audience? Any more questions? I have a question. Óscar, for the electronic missing, are you having some missing of perturbed mutual symmetry or some co-maximal symmetry?
Well, here, in this talk, I'm not talking very much about the in particular symmetries. We have been looking at several symmetries, several discrete symmetries that are used typically to determine the neutrino masses. We have been, there is a paper that we are finishing to write. I wanted to have sent it before the talk, but I could not. There were some last-minute problems that we more or less have solved. But here, for instance, this is an A4 symmetry. In A4 symmetries, typically not with this. These orthogonal flavons would be the ones responsible for the charged leptons, not for the neutrinos. But I can still get the same alignment 1, 1, 1, and things like that as I was doing before, just because this was a simple case example and I didn't want to. But we did this we have done it with A4, A5, T7, T13. We have tried, we have been investigating, and Delta 27 also. There are different problems. Here I'm doing a very particular scalar superpotential, if you want, to get these things. And here we can prove it easily. There are problems. I didn't tell you before, but I had this problem here. I was showing here how to get an preserve exactly the alignment, not perturbatively, not for a small supersymmetric masses. No, for any mass. I don't care. Okay, that's what I have done so far. But that was possible if the supersymmetric potential was only quartic and quadratic. Okay, if I have a cubic term, then cubic and quartic potentials with the field scale differently, and it's not possible to get an exact solution. Still, we have been able to do something perturbatively in this limit, soft mass much smaller than the mediator mass, if you want, okay, or the flavon mass. In that case, we can do it. But yes, I mean, this thing that I was showing here is very useful, but in some cases it's not exact. You have to do it perturbatively for some symmetries. But we want to apply it to any non-supersymmetric model. That was the goal of the paper, to be able to do a simple alignment, a simple method of strategy to get the required alignment, even in non-supersymmetric models. If you have a supersymmetric model, but you put very large shot breaking, it's non-supersymmetric.
Yes, in that case, there will not be supersymmetric. And for the delta 27, for getting the alignment for this delta 27 triplet, I suppose that there will be more driving fields. Will be more.
Yes,
will be more complicated than the 94.
It's more complicated. It's more complicated. I am just showing a simple example, huh? But in principle, this kind of this method that I was doing here, in fact, first we did it for A4 exactly. We did the supersymmetric version, the F terms, then we put soft masses for SUSY breaking, and we minimized the full potential. We checked that the minima were the extrema were minima, everything. We did it deriving, making derivative. Then we found out this method that is a variation of a method that Ivo Barcelas and Igor and somebody else were using for a Higgs multi-Higgs model, not for these things, not for flavor, but for the alignment in multi-Higgs model. And we use their techniques to do these things, and we can do it in this case if it's only quadratic and quartic exactly, which is very nice. But we have to try to expand it to other models. Although I was saying here, cubic and quartic coupling simultaneously are only possible if the field, whatever flavon field, is not charged under an additional discrete symmetry. If not, it's impossible to have an F term, say, linear and quadratic in the flavon field. But there are some models where this appears. And so that's why we discuss also.
See. More questions from the audience? If there are no more questions, we send the speaker again for the very nice and complete talk. Thank you very much, Óscar, for the very nice talk. Thanks a lot. Very nice talk.
Thanks for the opportunity to talk to you.
We are very happy. We are very happy to have a very nice seminar given by Óscar Vives, and we meet at the next seminar. Have a very nice afternoon, all of you. Nice evening, Óscar.
Okay, thanks. Bye.
Bye. Bye.
Bye.
Bye.